endocyclic bond 2 positions away. This and that are parallel, as are this and that. Equatorial parallel to the endocyclic bond 1, 2 positions away. Where is my equatorial here? Well, if my axle is down, equatorial is pointing up. Up and parallel to the endocyclic bond 2 positions away. Now, I'm going to draw it like this. And I could say, well, look, a parallel line could also be like this. Why did I draw it like that? Well, for 2 reasons. If I drew it like that, my bond angle is not 109.5. That's clearly less than 90. So that's a problem. But secondly, it's pointed towards the body of the ring. And they never point towards the body of the ring. That space in the middle is empty. So I know, although this is part of the parallel line, the same parallel line, this is not where the bond is. Because the bond angle is not 109.5. That's clearly less. And it's pointing towards the body of the ring. That can't happen. That's the same reason why I didn't do this for this one, because the bond angle here would have been less than 109.5, and it's pointing towards the body of the ring, so that can't be right. Okay. Where will this one be? Well, if my axial is up, my equatorial will be down. And it'll be down and parallel to this bond, and pointing away from the body of the ring, so it'll look like this. Where is this one? It'll be pointing up, parallel to this line or that line. Where is this one? Down, parallel to this line or that line, and away from the body of the ring. Where is this one? Up and away from the body of the ring, parallel to this line or that line. So that is what the ring, the chair, would look like. And again, these would be the axial bonds, and these would be equatorial bonds. Okay. Life would have been simple, but a lot less exciting if that's where the story ended. It turns out that the enhanced flexibility in the cyclohexane allows it not only to exist as the boat and as the chair, but it allows the existence, as it turns out, of 2 distinct chairs. 1, 2, 3, 4, 5, can't count. So here's what we're going to do. So we're going to build our chairs, and I'm going to tag 2 groups in the chair. So I'm going to so here's my boat. I'm going to pull that down to make the chair. And I'm going to go ahead and put red walls on some axial positions. So I'm going to make the same thing. So I'm going to put the red globes on the axial positions. And I'm going to make them the 1, 4 positions. And I'll take some white ones and put them in the corresponding equatorial positions. So red is axial, white is equatorial. Red is axial, white is equatorial. So these 2 that I've built, stop it, these 2 that I've built are exactly the same. They're equivalent structures. Strange. Okay, so these are equivalent structures, right? Equivalent structures. Remember, red is axial, white is equatorial. So I'm going to take this chair, right? I'm going to take my chair, and I'm going to grab carbon 1 and 4, which is the easiest way of doing these rotations. And I'm gonna make a boat. So I'm gonna bring carbon 4 up into the boat, and we'll take carbon 1 away from it. Okay? So when I do that, what I've done is made a chair, but now the whites are axial and the reds are equatorial. This is very different from this structure, where the reds are axial and the whites are equatorial. And even though I turn it upside down, they're not the same. These are not the same structures. This chair is very different from this chair. Right now, of course, I've tagged the groups. If these were all H's, the two chairs would be indistinguishable from each other. They'd have exactly the same population density in a sample. But once I tag groups, that creates a frame of reference, and my chairs are not necessarily equivalent to each other. Okay? So this process in which I'm doing a rotation from a chair to a chair is referred to as a ring flip. Right? When I rotate to go from chair to chair, it's called a ring flip. And the question we're going to immediately ask, which is the question we asked last day, looking at the anti and gauche and fully eclipsed conformers, is what are the relative energies? Once I am creating subspecies, we talk about chair versus boat, and the boat was less stable because of torsional and bowsprit interactions. Okay? We talk about the relative energies of those subspecies, because that impacts the population density. The system is going to shy away from the boat. There'll be fewer boats, fewer molecules in a boat conformer than I have in the chairs. Well, that's great. But what about the two chairs? If there are two different chairs, which, if I substitute the molecule, may give rise to two entirely different subspecies, what are the relative energies? And more to the point, what are the factors that affect the relative energies? And how do those factors relate to what we did in the last lecture? Because the relative energies of the anti and the gauche and the fully eclipsed had to do with the angle of rotation and the sizes and therefore spatial orientation of the groups. It had to do with steric interactions. So what we'll do in the next lecture is pick up on that and look at the fact we're going to tease out the relative energies of our chair conformers. We know the chairs are better than the boats. No angle strain, at least in cyclohexane itself, no torsional strain. But as we substitute the chairs and we create two different chairs, what are their relative energies? And how do steric factors play a role in determining their relative energies and as a result, their population densities, right? Which one is going to be more abundant than the other? So we're going to look at the interplay of those factors in the next lecture. Thank you.